Sorry, normally I have a very loud voice. I don't use a microphone, but I lost my voice 3 days ago. So if you can't hear me, get closer. That's the best advice I can offer. So sorry if you can't hear me, seriously. I'll do my best to actually speak into the mic, which I normally have a bad habit of not doing. You're good? If the guy in the back can hear me, I assume everyone else is good. All right, awesome. So again, I always preface, whenever I give a talk at a Python conference, I feel like I always have to preface this, like, don't beat me up. I'm an R guy. I think James purposely has me speak at Python conferences to try to get the R out of me. It's not going to work. He's in the room next door. I wish I could hear him speak. I wish he could hear me speak because we like having fun busting each other's balls. We really give each other a hard time, but it's fun. There's lots of room for different languages. I know later today there's a talk about Julia and Python. I'm not even going to touch that one. So in fact, today I'm not going to talk about programming at all. Nice. Yeah. Yes. I'm here to talk a little bit about math. Yeah. And with that enthusiastic response, I'm hoping what I'm talking about is high level enough. I'm hoping this isn't like arithmetic. We'll find out. So today I'm actually really here to talk about the lasso. Yeah, come on guys. I can't speak, make this interactive. So who here has heard of the lasso? All right, I have a feeling this talk's going to be under your heads then at this point. So sorry if this is low level. So I tried looking for a picture of John Wayne throwing a lasso, but I couldn't find John Wayne. I had to settle for a generic cowboy. But the lasso is an invention of these professors out of Stanford named Hastie, Tibshirani, and Friedman. I'm sure a lot of people here have heard of them, right? Is that sarcastic? It sounded sarcastic. It is Aaron. I know him very well. That's why I thought it was sarcastic. Okay. So these are, if anyone's ever heard of the book Elements of Statistical Learning, one of the books about data mining, or their new book, Introduction to Statistical Learning, that's them. They're prolific. They're actually biostatisticians. One's a biostatistician. None of them are actually statisticians. They're all like from other fields. But they're just frickin' geniuses of the stuff they came out with. They came out with generalized additive models. Anyone's heard of those? They came out with, obviously, the lasso and some other things I'll talk about. They came out with, now I'm drawing a blank, but they came out with, they're like up there with Bradley Efron. Everyone knows Bradley Efron. He came up with the bootstrap. These are like the next generation Bradley Efrons. And they teach a class every summer, like 2-day class for like $1,500. This year it's in Boston. While I don't really propose people go to Boston, it'd be really cool to see them speak. No Yankees fans? Seriously? That just fell flat completely? All right. So, get him. So the lasso, I saw who knows the lasso. Who does not know the lasso? It seems like the same people raise their hands.
We've heard of it, but we want to learn more. We don't understand.
Nice. All right, so the lasso is an extension of regression. I assume everyone knows regression, right? All right, awesome. So basically, you're just fitting a straight line through a cloud of points. There is going to be some R.
Just the results, not the actual.
You won't see a single line of code.
I use about 1,000 lines of R a day and about maybe 1 or 2 for Python.
Okay, so you're on my side. You're my bodyguard today. Cool. ggplot, I'm a huge fan of ggplot. I know there is a port of ggplot to Python. There's 2 ports, actually. I don't know the names of them. So one's called ggplot. The other one's called Boku or something. I don't know. But they work fairly well from what I've heard. So this slide is supposed to have math on it. Tell you what, everybody. I'm going to refresh the browser so you can see my math because there's a lot of math. Give me 1 second here. Sorry for the technical glitches, but, stuff happens. Oh, is there not an internet connection? No? Well, that's disappointing. Let me try one other thing, because I want everyone to be able to see this, because the math is why we're here, right? It was literally working. Oh, hold on, wait a minute. I do. It's all you poor bastards. Why is this frozen? Hold on.
There's whiteboard or paper behind you.
It might come to that. We might have a cool interactive math lesson here. Let me just try one more thing. Sorry. There we go. Let's try this. All right, put that back up there, refresh it. All right, who reads LaTeX? Seriously. Nice, all right, so translate this. What is this? Okay, we have y equals x beta plus epsilon. Oh, it's processing. It's slowly coming at 0%. Fantastic internet connection. Basically, it's y equals x beta plus epsilon. You have your predictors, your x, your design matrix, times the coefficients beta plus a random noise term. Okay, that's the top line. Failed to load? What the hell? All right. It's Chrome.
It's probably because you're accessing as a file instead of.
We can.
Maybe you should use Python.
You should use Python to run a local web server. Yeah.
Is anyone in this room who can help me with that?
You can do it in R too, I guess.
Anyone see my mouse? Damn it. All right, well, guys, we're going to do our best here. We're just going to pretend. I'll talk about the math. And Aaron, did you find the whiteboard?
Right here.
All right, we might just use that. Let's see. All right. You know, if we have to do it, we'll do it. I'm a team player here. All right. Did you find a marker?
Yep, right there.
Oh my God. All right.
I'll extend that one.
Yeah, try that one. All right. So everyone knows this, right? All right. So essentially, it's y1, y2, yn equals. You have a column of ones for the intercept. This really sucks with my voice. x1, xp, so forth and so on, times beta. Everyone knows that, right? No big deal? All right, awesome. So essentially, you have your response vector, y. I call it response. I call the x's predictors. I know a lot of people in social sciences call them independent variables and dependent variables, but that violates probability theory. If x is independent of y, y has to be independent of x. You can't have independent and dependent. It really bothers me. That's my rant for today. All right. So beta, you solve for beta. Gosh darn it. All right. Okay. Everyone's seen that? X transpose x, inverse x transpose y. Everyone knows that, right? Fairly easy to solve. You get to a large matrix, it could be hard to invert it. I think a 10,000 by 10,000 is like the biggest they've inverted recently. Right? It's kind of hard. So you don't actually invert it. You do a Cholesky decomposition or you do a QR decomposition. You get an approximate inversion, whatever it may be. Not the hardest thing to solve. And use LAPACK libraries to take care of this. You do it in R, you do it in Python. It's probably using very similar matrix algebra libraries underneath, whatever it may be. But now we get to the question of which variables matter. This is a sample data set I have. It's from essentially the census, the American Community Survey. You have all these different variables. This is just a small set. This is what I can fit on the screen in a pretty format. There's like 100 variables here. How do you choose the important variables? This is the results of two different regressions. One on the left used a lot of variables. One on the right used fewer variables. Well, how do you decide which set of variables to keep? The one on the left, if you use too many variables, there's overfitting. Who here is concerned about overfitting? Nice. I like these people statistically inclined. I like this crowd. Who's at James Talk? Are they all like more just programming geeks? All right. So you have overfitting. That's why the confidence intervals are so wide. You have overfitting or get very uncertain estimates. If you come on the right, by leaving some variables out, the value of the coefficients for the variables that stay in changes. So you can't ever look at the variable by itself. Some people say, look at the results and check the p-value of each individual coefficient. The p-value isn't good, throw it out. First of all, p-values suck. I'm saying this now. You guys all look like more modern machine learning people than old-fashioned statisticians. Sorry if there's an old-fashioned statistician here. But as a pseudo-Bayesian, or I like to pretend I'm a Bayesian at least, I don't like p-values. Ronald Fisher came up with them about 100 years ago arbitrarily. He arbitrarily picked out 0.01, 0.05, and 0.1. All right? They served a purpose back before we had computers. Nowadays, you don't really need them. But anyway, you can't look at them. Let's say even look at the confidence intervals individually. You can't do that because if you take out one, you affect all the others. You take out one variable, all the rest will change. So we need to find ways to choose these variables. All right? Common techniques in the past was forward stepwise selection. Right? Everyone knows forward stepwise. You start with one variable, you add two, you add three, you add a different one. You keep building and building it up. Its reverse is backwards elimination. Yes, the stairs go different directions, by the way. That took a lot of work using Microsoft Paint to flip it around. So backwards elimination, you start with all the variables and you slowly eliminate them. And you take them all away until you get to a happy point. And the composite of that, stepwise, forward and back. Yeah, I had to search the internet long and hard for this one. Escher, yes. Yeah, how can you beat Escher? Right? This is essentially what you do. You add a variable, you take away. You add, you take away. You go back and forth. It's this tug and pull. It goes back and forth. Okay? Yes?
So why can't you just take every possible combination, like 100?
Like all subsets? Yes. So the way this works is, though, if you do all subsets, the number of combinations is like this. Okay? You have p choose 1 variables plus p choose 2 plus p choose 3, 4, etc., etc. This comes out to be 2 to the p minus 1. So if you have just 10 variables, all subsets, you're going to have 1,023 combinations. Even with modern computers, if you have a lot of data, this can still take a long time. And that's 10 variables. When's the last time you got a data set with just 10 variables? Right? And I tried doing the calculation for 100 variables, but it's like billions of combinations. I'm the one without a voice. You can speak.
I think there's way more.
But there's trillions. I just couldn't keep track of how many commas there were. Yeah, a shitload. Sorry if I offend people by cursing, but I grew up in the music industry, so cursing's like my default. So I'll try to keep it to the minimum. So we have all these different things, and all subsets used to be a legitimate way to do it when you had 5 variables. But then again, you're doing it by hand, so it sort of sucked. But you need criteria to decide how you choose your model. Since you don't want to look at each variable individually, you fit a model of 5 variables, you fit a model of 6 variables, and you compare them somehow. So common criteria are AIC, BIC, and deviance. And there's other ones too, but these, I don't want to talk about malloc-p. Right? At this point, that's old-fashioned. Everyone know AIC? It stands for IKK, information criterion. It's something like -2 times the log likelihood plus a penalty term, I forget the penalty term. It's 2p, I mean. BIC, they like to claim it stands for Bayesian information criterion, but it just really is the one that came after AIC, so it's called BIC. There's also CIC and DIC, and I'm not kidding. BIC is same as -2 times the log likelihood plus 2 log NP, something like that. I might have made that one up. It's in my book. Hey. Whoever wins this afterwards can look up BIC and AIC. It's in there somewhere. So we'll look it up later because I'm running out of time, so I can't look it up for you now. And if you don't win, buy my book. So all these things are all well and good. If you have tens of variables, you can see it's 1,000 combinations. But you might get hundreds of variables. You might get thousands of variables. All right? So we need to deal with this. Especially when you get to all these variables, you run into the curse of dimensionality. Who here has heard of the curse of dimensionality? All right. It basically says when you have too many variables, things go awry. Now I will say there are some people, my former professor Andy Gelman, like to say it was the blessing of dimensionality. Yes, he's a big thinker in multi-level models. So if you have a multi-level model, you could add extra structure. You have more variables, you have more structure. But if you're a machine learning person, you just want to throw all the variables into the computer. You don't want to have to think about it. Andy Gelman's one of those really thoughtful statisticians. He'll put a variable and think about it, then take it out. Really, everything's very conscientious. As opposed to machine learning, we're throw everything at the machine, let the machine do it, right? So we need to worry about the curse of dimensionality. We can illustrate this with one of my favorite things. I really wish James was in the room because he loves it when I say multi-dimensional hypercube. But that's how you have to imagine this. This is just a regular cube, but you could extend this into, you keep going orthogonal, and you can make this into a hypercube. Right? They're awesome, right? Yeah, they're a lot of fun. Yeah. Carl Sagan has a great description of flatland and hypercubes. You've seen that video. It's awesome. All right. So imagine the cube itself is your data, right? And the small cube is your local neighborhood for a local method, local weighted regression, something. And in order to grab a certain percent of the data, the cube needs to be a certain size. Because as you get into this bigger space, multiple dimensions, the data is very sparsely distributed. All right, so you can't really use local methods that much. And so it works out something like this. The x-axis is the fraction of the volume of data you want to capture, and the y-axis is the how big the subcube has to be. So once you get to 10 dimensions, if you want to capture even 10% of the data, you need to have a cube that's 80% the size of the whole data. So you no longer have local methods. You have to look at the whole data set, all these multiple dimensions across the whole length of them. So it becomes very problematic. It's especially problematic. Oh, but I stole this picture. I stole this picture from Hastie and Tibshirani's book. This picture I recreated using R. I had to play it. This becomes a real problem when you have large data. You get into large data and you get issues. Yeah, this is large data.
Feels like that.
So this is where shrinkage and regularization comes in. These are terms. Shrinkage is usually used in a Bayesian sense. Regularization is more of like a machine learning or frequentist sense, but essentially doing the same thing. You want to reduce your dimensionality, shrink down your variables, shrink down the coefficients. So first up is the ridge, which is displayed by this equation. Since we are in a bit of a bind for time, I ran a little long earlier, I'm just going to skip ahead to our friend, the lasso. All right? And essentially what this is doing is you're trying to minimize the normal regression curve. Hold on. That's your prize. Oh, he's selfless. I like this guy. So you're essentially, oh man, I wish I could see this. All right, you're essentially trying to minimize the sum yi minus xi transpose beta squared plus lambda, the sum of beta j absolute. That got really messy. Essentially, you're trying to minimize the normal least squares criterion plus this penalty term, which is lambda, your tuning parameter, plus the sum of the squares of the betas. All right, it's a way to keep the coefficient small. This you can see this shows both lasso and ridge. So lasso is, whereas ridge is, that's the main difference, right? The ridge is an L2 penalty, the lasso is an L1 penalty. Visualized, they look like this. Essentially, this is the decision boundary. The ridge is on the right-hand side. It's this nice circle. It's a smooth decision boundary, whereas the lasso is on the left-hand side. It's very sharp angles. The ridge, the coefficients get spread out, whereas the lasso just throws out variables. That's key. It zeroes out variables. It's like variable selection. The lasso is essentially variable selection. You throw out 1,000 variables, it'll come back with you in a situation, it'll give you 10 variables or 15 or whatever. It's great at that. And that's because of the sharp angles you see in the diamond. And traditional regression methods requires that you have more rows of data than you have columns. But with the lasso and the ridge, well, I don't want to claim the ridge, definitely the lasso, it can work with when you have more columns than data. It can work in a situation where you have many more columns than data. It's amazing. I saw an example that benchmarks was 5,000 rows, 20,000 columns. And it worked fast. It's a really fast algorithm. So the elastic net, which is a really complex equation, yes, that's in here too if you want to look it up. The elastic net is a dynamic combination of ridge and lasso. Basically takes the two penalty terms and blends them. I'm sorry, I keep like puffing on this thing. There you go. It's a dynamic combination. There's a little bit of a lasso penalty, a little bit of ridge penalty, and using the alpha tuning parameter, you can decide how much lasso and how much ridge. And you can sort of fiddle with it a little bit. I'm not going to write down these equations because it's a long time to write, and you can look it up right here. We'll just assume it's a cool equation. It's actually my favorite equation too. I have my business cards designed by one of my students, graphic designer, and she had a blackboard in the back of all my favorite equations, and this is one of them. I'm a nerd. Pot calling the kettle. Anyway, so that's the elastic net. Now this could take on the whole GLM family. It could do Gaussian regression, which is normal regression. It could do logistic regression, Poisson regression, my favorite type of regression, multinomial regression, survival models, I'm flying through this, guys, and multivariate Gaussian regression. All these images are drawn in R, just FYI. So, some features of the lasso. It's great for it's actually incredibly fast. It's the same speed as fitting a regular regression. It works when P is much greater than N, and it does variable selection and makes for stable predictions. I'll be happy to talk to anyone afterwards. I have 5 minutes. If I skip anything, I'll be happy to talk to you afterwards if my voice holds out. It fits a coefficient path like this. Each of these lines represents a variable, and as it goes on, depending on your value of lambda, the value of the coefficient changes until it gets to 0. When it comes down to it, though, you get a bunch of coefficients that it chose. But notice there's a coefficient plot I showed before. What's missing on this coefficient plot? Error bars. it's very difficult to get error bars, standard errors, confidence intervals from the lasso regression. But sometimes you need inference, especially if you're doing like a medical study or anything like old-fashioned statistics kind of, you need inference. So luckily there's been some steps taken in recent years to build confidence intervals and significant tests for the lasso. Sartori and Milani in 2009 came up with a bootstrap confidence interval, and this is a beautiful set of equations. My talk is online. I highly recommend you go check out these equations. They come up with, I only have enough time to explain this, so sorry. Basically, they use the bootstrap. Everyone knows the bootstrap? All right, hopefully everyone does. The bootstrap essentially is a way of resampling the data. Problem is, though, while it gives you these confidence intervals, people say there's an issue with the bootstrap with a biased estimator, and the lasso is a biased estimator. You reduce the variance by taking on more bias, and bootstrap has a problem with biased estimators. They might have a way to use like a thresholded beta to get around that. It's still not the best, though. So fortunately, the guys who created the lasso, Hastie and Tibshirani, they came up with a covariance test statistic, which is a beautiful equation. It's even better than the bootstrap one. It uses inner products. Basically you're comparing like your coefficients for like at lambda k plus 1 with the active set of variables for the coefficients at lambda k. That did not make any sense the way I explained it. It makes a lot more sense with the math on the screen. Basically you're saying the coefficients now and the coefficients we added one more variable. And it's a brand new thing that came out with it, I think last year. It was like huge news. Everyone's so super excited about this. Unfortunately, you can't see my math, but I promise you, if anyone has a smartphone, go to slide 37. It's right there. I should have told you guys this like 10 minutes ago. It's all online. Anyway, so next steps in this. And we want confidence intervals, not just, so right now it only works for a Lars regression, a least angular regression, which is essentially a lasso. But they haven't done it for the elastic net yet. I'm hoping they'll do it for elastic net. I asked them to do it. They said, we'll try. And also, if you have confidence intervals for the coefficients, you really want it for your predictions. You want prediction intervals. That's going to be really, really important in the future. Unless you're like doing a marketing thing where your predictions only matters for 1 second or half a second, you really need to have prediction intervals. So with that, I've got 1 more minute. So any questions? jaredlander.com/talks.
Are you selling a book?
What?
Are you selling a book?
I'm giving away 6 copies, and then just go to Amazon to buy my book. Yes. Cross-validation. Yeah. Use either MSE or deviance using cross-validation, even AIC using cross-validation. Yeah. Yes. Ridge. So the elastic net, if you set alpha to 0, it's ridge. Now, I haven't seen any work done from Hastie and Tibshirani about doing significant tests for the ridge, but this bootstrap method should work for the ridge just as well as it worked for the lasso. Oh, you're not doing this inversion anymore. Yeah. Plus, when it's done selecting the variables, it selects fewer than there are rows. It will never select more variables than there are rows. Resampling. Mm-hmm. I think you still have issues with bias, though. I think so. Yeah. Someone in the back? I believe scikit-learn has it. And the GLMNet, which was written by Hastie Tibshirani, this last question I think I'm going to get booted. I'll ask everyone else to ask me questions in the hallway. I'll be happy to talk. There's GLMNet. They wrote bindings for R and for MATLAB. But I believe using Python, whatever you guys call it, you probably could do shared memory because it's all written in Fortran. So if Python can talk to Fortran, you could do it. And if you wrote that library, you'd be like the goddess of like the Python community probably. There you go, scikit-learn. Oh, cool. But it wasn't written by these guys. Okay. Okay, that's cool. And with that, I think I'm getting the boot. Okay. Thank you. So if everyone wants, I'll be on the hallway answering questions. I'll autograph and give away 6 copies. I don't know how I'm going to give it away, but whoever asks me the